Somewhere tonight, a planet is slipping free of its star, drifting past the orbit of a world that used to be its neighbor. It takes only a sliver of extra speed to cause this, barely more than what a planet needs to break away forever. But here is what most people get wrong about losing a star. It is not rare, and it rarely looks violent at all. It may be one of the most ordinary things that happens to a world like this one. And once it happens, that world does not vanish. It keeps existing, alone, for longer than most stars survive. If you enjoy deep space and science content, do me a small favor, hit that like button and subscribe. It genuinely helps this channel grow, and there is much more like this coming. Make yourself comfortable. Let's begin. That is the strange truth sitting at the center of tonight's subject. A world can lose its star and keep going, not for a moment, not for a human lifetime, but for stretches of time so long that entire species could rise and vanish before that world ever changed course again. For most of human history, nobody imagined this was possible. Stars held their planets the way a hand holds a stone. It seemed permanent. It seemed unbreakable. It seemed like the most solid fact in an otherwise uncertain universe. And then, slowly, over the last few decades, that certainty came apart. The first person to take the idea seriously in print was a planetary scientist named David Stevenson. In 1999, in the journal Nature, he proposed something that sounded, at the time, almost like fiction dressed up as science. He suggested that a planet without a star might not be a dead planet at all. If it held on to enough internal heat and wrapped that heat in a thick enough blanket of hydrogen gas, it could, in theory, keep an ocean liquid beneath its surface indefinitely, with no sunlight ever reaching it. In simple terms, he was suggesting that warmth does not have to come from above. Sometimes it can come from within, quietly for billions of years, long after the light has gone. For over a decade, Stevenson's proposal remained exactly that. A proposal. There was no way in 1999 to actually find one of these worlds. A planet with no star produces no light of its own worth speaking of, and it reflects nothing, because there is nothing nearby bright enough to reflect. To put this in human terms, searching for one felt a little like searching for a single unlit window in a city with no streetlights, using a telescope pointed at the wrong side of the block. That changed in 2011. An international team led by the astronomer Shinichi Sumi published a paper in Nature describing something nobody had confirmed before. Direct evidence that these starless planets were not just possible, but common. And they did not find them by looking for light. They found them by watching for a very particular kind of shadow. The method is called gravitational microlensing, though the name matters far less than what it actually looks like through a telescope. Somewhere in the galaxy, a distant ordinary star sits quietly in the field of view, night after night, its brightness steady and unremarkable. Then, for a matter of hours, sometimes only minutes, that star brightens. Not because anything happened to the star itself, but because something invisible passed almost exactly between it and Earth. An object with enough mass to bend the light around it like a lens, focusing that starlight, making it flare briefly before fading back to nothing unusual at all. There is no second act. Whatever passed in front of that star will likely never cross in front of anything we can see again. In simple terms, astronomers are not looking for planets directly. They are watching for a single flicker in a field of otherwise motionless stars, and inferring from the shape and length of that flicker that something with no sun of its own briefly crossed the light on its way toward nowhere in particular. It is a strange kind of proof. You never see the object itself. You only see the absence it leaves behind, in someone else's light, for a few hours before it is gone completely. And yet, using exactly this method, Sumi's team arrived at an estimate that reshaped how astronomers think about the galaxy. These starless, lightless planets may outnumber the stars of the Milky Way itself. Not planets that orbit something and simply went unnoticed. Planets with no star at all, drifting through the space between the ones we can see. Consider what that means. Every star visible in a clear night sky, every single point of light overhead, may have less company than the darkness surrounding it. For every star burning steadily in that sky, there may be several worlds nearby, with no sky of their own to burn in at all. So the picture that emerges from this early research is a quiet correction to something almost everyone assumes without ever examining it. A planet is not a permanent resident of its solar system. It is closer to a temporary guest, one that can, under the right circumstances, be shown the door without warning. And once shown the door, it does not cease to exist. It simply continues, cooling, drifting, alone, somewhere far past the last light of the star that once held it in place. This raises the obvious question that Stevenson's paper never really answered, and that Sumi's discovery only deepened. If these worlds are out there in such numbers, something must be causing this to happen, over and over, throughout the galaxy's history. What, mechanically, does it actually take for a planet locked in orbit for billions of years to suddenly find itself free? What, mechanically, does it take for a planet locked in orbit for billions of years to suddenly find itself free? The answer begins with a number most people already understand, without ever putting a name to it. Everyone has watched a launch on television. A rocket climbing, slowly at first, then faster, straining against something invisible that wants to pull it back down. That invisible pull is gravity, and the reason the rocket eventually stops straining and simply leaves is that it crosses a threshold, a specific speed. Below that speed, whatever goes up must come back down. Above it, the object is gone for good, sliding free of the planet's grip and out into open space. That threshold has a name: escape velocity. For Earth, it happens to be about 25,000 miles per hour. Below that, a rocket falls back. Above it, nothing calls it home again. A planet orbiting a star obeys the exact same rule, just at a far larger scale. The star's gravity is the hand holding the stone. The planet's orbital speed is what keeps that hand from pulling it all the way in. As long as the planet's speed stays within a certain range, it keeps circling year after year for as long as the star exists. But if something pushes that speed past the star's own escape velocity, the hand simply cannot hold on any longer. The planet does not fall away slowly. It leaves. The obvious question, then, is what could possibly deliver a push that large? Planets do not accelerate on their own. Nothing detonates, nothing explodes. In simple terms, the answer very often comes from a neighbor. A larger planet, sharing the same system, close enough for its own gravity to matter. This is the same principle behind gravity assist maneuvers, the technique that spacecraft engineers already use on purpose. A probe flies close to a planet, borrows a small amount of that planet's orbital momentum and leaves the encounter measurably faster than it arrived. It is a real and well-understood transfer of energy, used deliberately for decades to send spacecraft farther than their own fuel could ever carry them. Now imagine that same transfer happening by accident, at far greater intensity, between two planets instead of between a planet and a spacecraft. If a smaller planet drifts too close to a much larger one, the larger planet's gravity can fling it outward with tremendous force. The same physics as a gravity assist, only violent, unplanned, and often final. Sometimes the outward push is only partial, and the smaller planet is thrown into a wider, stranger orbit. Sometimes the push exceeds the star's own escape velocity entirely, and the smaller planet simply keeps going. Past the outer planets, past the edge of where the star's light still means anything, out into the dark between systems, where it will spend the rest of its existence. Astronomers call this general process planet-planet scattering, and the mathematics behind it have been understood for decades. What changed the conversation was applying that mathematics to our own solar system's deep past. In 2011, the astronomer David Nesvorny, working from simulations at the Southwest Research Institute, proposed something that unsettled a number of his colleagues. He suggested that our solar system, in its earliest few hundred million years, likely contained a fifth giant planet, a world roughly the size of Uranus or Neptune, orbiting the young Sun alongside Jupiter, Saturn, and the two ice giants we know today. According to Nesvorny's modeling, that fifth giant did not survive. Roughly 4 billion years ago, as the orbits of the outer planets shifted and settled into their current arrangement, a close encounter with Jupiter delivered exactly the kind of gravitational push described a moment ago. The fifth giant was accelerated past the Sun's escape velocity, and it left. Not destroyed, not broken apart. Simply gone, ejected into interstellar space, where it presumably still drifts today, cold and starless, somewhere among the countless other wanderers already described. Consider what this means for the story being told tonight. This is not a hypothetical happening to some distant, unfamiliar star system. Nesvorny's simulations suggest it happened here, in the same gravitational neighborhood currently occupied by Earth, to a planet that may have formed from the same disk of gas and dust that eventually became everything familiar in the sky. The solar system, as it exists now, may be the surviving arrangement left over after a member of its own family was quietly removed. This is worth sitting with for a moment. 4 planets remain, gas and ice giants sitting in careful, stable orbits, appearing as permanent and settled as anything in nature can appear. And yet, the current arrangement may only be the result of one planet losing a gravitational contest that took place before the Sun was even 1 billion years old. Stability in this light does not mean nothing happened. It often means the disruptive event already occurred, long ago, and everything visible today is simply what was left afterward. In late 2013, this theoretical framework met something closer to direct observation, in a discovery that unfolded far from any planning committee's expectations. A team using the Pan-STARRS 1 survey telescope in Hawaii, built primarily to scan the sky for potentially hazardous asteroids, noticed something in their data that did not match anything they were looking for. A faint object glowing dimly in infrared light, with no visible star anywhere near it. Follow-up observations confirmed what the team suspected almost immediately. This was a planet, roughly 6 times the mass of Jupiter, young by planetary standards at only around 12 million years old, and entirely alone. The object received a formal designation, PSOJ 318.5-22, a string of numbers and letters that does little to convey what the discovery actually meant. Here was a planet, fully formed, glowing faintly with its own leftover formation heat, drifting through interstellar space with no star to call its own. Not theorized, not simulated. Observed directly, sitting in the data the same way any other confirmed object would. In simple terms, PSOJ 318.5-2 gave the entire idea a face. Before 2013, the ejected planet was mostly a mathematical inference, built from statistics and probability distributions and simulations like Nesvorny's. After 2013, it was a specific object, with a specific brightness, a specific estimated mass, and a specific patch of sky where astronomers could point a telescope and see, with their own instruments, exactly what a starless planet looks like. What it looks like, it turns out, is almost nothing at all. A faint smudge of infrared light in an otherwise empty stretch of sky, distinguishable from the background only because its own residual heat, left over from its formation, still glows faintly enough to register. No reflected daylight, no twilight, no dawn, just a planet's own leftover warmth, radiating slowly out into a darkness with no edges. This is where the 2 threads of tonight's subject begin to meet. The theoretical mechanism, gravitational scattering violent enough to exceed a star's escape velocity, explains how a world like this comes to exist. The observational record, planets like PSOJ 318.5-22, and the broader population estimated by microlensing surveys, confirms that it does happen again and again throughout the galaxy's long history. What remains is the harder question. Understanding how a planet leaves its star is one thing. Understanding what actually happens to that planet afterward, in the years, centuries, and eons that follow, is another question entirely. And it is a question that reaches into some of the coldest, strangest physics in this entire subject. Understanding how a planet leaves its star answers one question. It does not answer the harder one. If this happens as often as the evidence suggests, something about the early life of planetary systems must make it almost routine, not a rare accident, a pattern, repeating quietly across billions of years and billions of stars. The scale of that pattern is worth sitting with slowly. Sumi's 2011 estimate, the one built from years of microlensing observations across the galactic bulge, suggested something specific. For every main sequence star in the Milky Way, there may be roughly twice as many free-floating Jupiter-mass planets drifting nearby with no star of their own. Consider what that ratio actually means. On a clear night, every star visible to the naked eye represents, statistically, perhaps 2 unseen worlds nearby, cooling quietly in the dark between one point of light and the next. This estimate did not emerge from guesswork. It came from a specific methodical survey, years of nightly observations of the same crowded stretch of sky near the galactic center, watching for the brief flickers described earlier. Each flicker, each microlensing event, became a single data point, and when astronomers gathered enough of these points and modeled what population of objects could produce them, the resulting number was larger than almost anyone expected going into the study. Simulations of early planetary system formation help explain why. When a new solar system is forming, the process is not tidy. Planets do not settle gently into their final orbits from the moment they form. In simple terms, a young planetary system is closer to a crowded room during the first uncertain minutes of a party, before anyone has found their seat. Orbits shift. Larger planets migrate inward or outward as they clear debris from their paths. Smaller planets, caught in that migration, can be pulled into unstable orbits, flung inward toward their star, or thrown outward past its gravitational reach entirely. Models of this early instability, run by multiple research groups over the past 2 decades, suggest that a significant fraction of planets formed around any given star may not remain there. Some fall inward and are consumed. Some are ejected. The remaining, more stable population is not the whole story of a system's youth. It is only what survived it. This reframes something people rarely think to question. When looking up at a well-behaved solar system today, its planets circling patiently in fixed, stable orbits, that stability is not the beginning of the story. It may be the aftermath. What remains after the young system already thinned out its own excess. The quiet, orderly system observed today may simply be what was left over once the unstable candidates were already removed. For context, this searching effort is only just beginning to reach its full potential. The Nancy Grace Roman Space Telescope, currently in development and expected to conduct one of the most extensive microlensing surveys ever attempted, is specifically designed to detect far more of these events than any previous instrument. Once operational, it is expected to substantially expand the confirmed population of free-floating planets, potentially detecting objects down to the mass of Mars, far smaller than anything found so far. What this means in practice is that current estimates, staggering as they already sound, likely represent only a fraction of what is actually out there. The true population of starless worlds drifting through the galaxy may be larger still, once instruments sensitive enough to see them are finally in place. If Sumi's ratio already suggested more rogue planets than stars, later surveys may only widen that gap further. Consider what this means for the night sky itself. Every constellation, every familiar pattern of stars overhead sits inside a much larger, much emptier field. A field where the true population of planets is not clustered neatly around visible stars, but scattered, mostly invisible, through the vast, dark spaces in between. The sky people have always considered a sky of stars may, in truth, be a sky of far more planets than stars. Planets that simply can't be seen at all. This is where the story reaches its quieter, more uncomfortable turn. The question is no longer whether losing a star happens. The evidence already answers that. The harder question is what happens next. What does existence actually consist of for a planet that has already lost the only source of light and warmth it ever had? Almost nothing written about rogue planets stops to ask this directly. Papers estimate populations, surveys count events, simulations model the moment of ejection itself, the violent gravitational handoff that sends a world past its star's escape velocity. But very little of that research lingers on what comes after, on the actual ongoing condition of a planet that has already left and will never return. That condition unfolds in a specific order, governed by simple, well-understood physics. It does not happen all at once. It happens gradually, in stages, the way a house grows cold after its heating system fails. Not instantly dark and frozen, but room by room, hour by hour, in a sequence anyone could predict once the underlying mechanism is understood. The first thing to go is warmth, not because the planet cools instantly, but because it loses the one thing that was replenishing that warmth continuously. A star does not just illuminate a planet, it maintains it, holding a stable thermal gradient in place across its entire surface, day after day, for as long as the star exists. Remove the star, and that maintenance stops. What remains is only what the planet can generate or retain on its own: residual heat from its formation, and whatever internal radioactive decay continues quietly inside its core. For context, Earth's own surface temperature depends almost entirely on the Sun's continuous input. Without it, calculations suggest the surface would drop toward the temperature of deep space within a matter of years, not centuries. The atmosphere itself would not simply grow cold and stay breathable. It would begin to fail as a gas altogether. This is where the physics becomes genuinely strange and worth pausing on directly, because it reveals something almost nobody considers when picturing a planet without a sun. The sky itself, the very air surrounding such a world, would not remain air for long. Gases condense into liquids and then solids at specific, well-documented temperatures. As a starless planet's surface continues cooling year after year, its atmosphere would begin falling out of the sky in a predictable sequence. Coldest gas last. Water vapor would condense first, forming ice at the surface. Carbon dioxide would follow, freezing directly into a solid frost. Eventually, as temperatures continued dropping toward the deep, unbroken cold of interstellar space, even nitrogen and oxygen, the very components of the air being breathed by everyone listening to these words right now, would begin to freeze and fall as a fine, pale snow. In simple terms, the sky would not simply darken. It would eventually come down, settling silently across the surface as a thin, frozen layer, coating what remained of the ground in something that used to be wind. This is the mechanism worth carrying into the next stretch of this story. Not an explosion, not a catastrophe, a quiet, orderly withdrawal of everything a star once provided, unfolding in sequence, gas by gas, until what remains is a world locked beneath an atmosphere that no longer moves at all. A quiet, orderly withdrawal, unfolding gas by gas, until nothing at the surface still moves. That withdrawal is only the beginning of the story. What happens beneath that frozen surface, in the years and centuries that follow, turns out to be far stranger than the freeze itself. Picture the sequence slowly, the way it would actually unfold, rather than the way a summary compresses it. In the first months after a planet crosses its star's escape velocity, very little would appear to change. Sunlight would simply grow fainter, the way daylight fades during a long, gradual sunset. Except this sunset would never reverse. Within a few years, depending on the planet's distance from its former star at the moment of ejection, that fading would become absolute. No dawn following, no warmth returning the next morning. Only the same dim, starless dark, night after night, indefinitely. Temperature would fall steadily during this period, following a predictable curve rather than dropping all at once. A planet does not lose its heat instantly, because its atmosphere and surface both retain some of that warmth, the way a covered pot of water stays hot longer than an open one. But retention only delays the outcome. It cannot prevent it. Over years, then decades, surface temperatures would sink further, passing thresholds that once seemed impossible to cross. This is where the atmosphere's slow collapse becomes worth describing precisely, because very few people, even those familiar with basic astronomy, picture what freezing air actually looks like in practice. Consider the order in which this would happen, because gases do not all freeze at the same temperature. Water vapor is the first to go, condensing out of the air and settling as frost, then as ice, long before the coldest gases even begin to react. Carbon dioxide follows next, and unlike water, it does something stranger. At sufficiently low pressure and temperature, carbon dioxide skips the liquid stage entirely and freezes directly into a solid, the same basic process that produces dry ice in a laboratory freezer, occurring here across an entire planet's surface instead of inside a machine. In simple terms, the sky itself would begin to fall in stages, coldest gas last, each one settling as a fine layer, on top of the layer that condensed before it. The final gases to freeze would be nitrogen and oxygen, the very components that currently make up most of the air being breathed by anyone listening to this right now. Nitrogen freezes at roughly -346 degrees Fahrenheit, oxygen at a slightly lower point still. These are not temperatures encountered anywhere on Earth's surface under normal conditions. They exist, briefly, inside cryogenic laboratories and permanently on the surface of a planet that has lost its star. Once temperatures fall this far, what once was air becomes something closer to fine, pale snow, drifting down through an atmosphere that no longer has enough remaining gas to carry wind. To put this in human terms, the very air filling a room would eventually become the frost coating its floor. What remains after this sequence completes is a surface locked beneath layers of frozen gas, sitting in absolute stillness under a sky with nothing left to move it. No wind, no weather, no cycle of any kind, because weather requires an active atmosphere, and an atmosphere requires enough remaining unfrozen gas to circulate. Once the air itself has settled onto the ground as solid layers, the very concept of weather stops applying to that world at all. Imagine for a moment standing on the surface of such a planet during the specific years just after the encounter that set it loose. This is not a distant abstraction. It is a physical sequence, and it would be perceptible, moment to moment, to anything capable of observing it. The sky would darken first, not suddenly, but the way twilight deepens on an unusually long evening, one that simply never resolves into either sunrise or true night as previously understood. Temperatures would drop steadily underfoot, the ground itself growing colder before the air fully catches up, because rock retains heat differently than gas. Within the ground, sensors, if any existed, would register a slow, continuous decline, week after week, with no plateau in sight. Eventually, a fine mist would begin condensing near the surface, almost imperceptibly, before settling as the first true frost. This is the water vapor stage, arriving early, while temperatures are still comparatively mild by the standards of what follows. Later, as cold deepens further, a heavier, almost imperceptible hiss would mark the carbon dioxide stage, gas transitioning directly into solid, coating exposed surfaces in a fine, crystalline layer. Later still, in the deepest cold, the last of the atmosphere would settle as the faintest, quietest snowfall imaginable, containing the nitrogen and oxygen that once made this world's air breathable at all. By the end of this sequence, the surface would sit in near total silence, beneath a solid sky, in temperatures within a few dozen degrees of absolute zero itself, the coldest physical state matter can theoretically reach. This should, by every intuitive expectation, be the end of the story. A frozen world, a dead world. Nothing left to describe beyond the temperature reading and the silence. And yet, this is precisely the point where a small number of researchers, working through the physics carefully rather than relying on the seemingly obvious conclusion, arrived at something genuinely surprising. Something that suggests the surface, however still and however cold, may not represent the entire truth of what continues beneath it. Because heat, it turns out, is not something a planet can only receive. Under the right conditions, it is something a planet can also generate, entirely on its own, indefinitely, with no star required at all. Heat, it turns out, is not something a planet can only receive. Under the right conditions, it is something a planet can also generate, entirely on its own, indefinitely, with no star required at all. This is the idea that quietly overturned the assumption that a starless world must be a dead world, and it deserves to be understood carefully, one piece at a time. Every rocky planet, including the one currently under everyone's feet, carries a small amount of radioactive material buried in its interior, left over from the same violent stellar processes that first forged the planet's raw materials. Elements like uranium, thorium, and a radioactive form of potassium sit embedded in the rock of the mantle and core, decaying slowly over billions of years, releasing a steady trickle of heat as they do. This is not a controversial idea. It is the same basic process that keeps Earth's interior molten today, roughly 4.5 billion years after formation, long after any heat left over from the planet's original formation should have faded to nothing on its own. In simple terms, a planet is not just a rock cooling passively in space. It contains its own small, extremely slow furnace, buried deep inside, quietly burning for billions of years, regardless of whether a star is anywhere nearby to help. The question, then, becomes what happens to that internal furnace once the star disappears. On a planet like Earth, radiogenic heat is only one contributor among several, mostly overshadowed by the enormous, continuous input arriving from the sun every single day. But on a planet with no star at all, that internal furnace stops being a minor contributor. It becomes the only heat source that still exists. This is exactly the possibility that the planetary scientist David Stevenson raised in that 1999 Nature paper described earlier, and it is worth returning to now with the fuller picture in place. Stevenson proposed that if a rogue planet retained a thick enough atmosphere, one composed largely of hydrogen gas, that atmosphere could function the way a blanket functions on a cold night, simply by generating warmth itself, but by trapping whatever warmth the planet already produces, preventing it from escaping into space as quickly as it otherwise would. Consider how a blanket actually works, since the comparison holds up surprisingly well under scrutiny. A blanket does not warm a sleeping body by producing heat. The body was already generating that heat on its own, quietly, through ordinary metabolism. The blanket's only function is to slow the rate at which that existing heat escapes into the surrounding cold air. Remove the blanket, and the same body, producing the exact same amount of heat internally, grows cold far more quickly, simply because nothing is holding that warmth close to the skin any longer. A sufficiently thick hydrogen atmosphere, according to Stevenson's calculations, could perform the same basic function for an entire planet. The radiogenic heat rising slowly from the interior would have nowhere fast to go, trapped beneath a dense atmospheric layer, insulated the way a blanket insulates a sleeping body from a cold room. Beneath that insulation, temperatures could remain warm enough, indefinitely, to keep water in its liquid form, sealed under a frozen surface crust, hidden from the starless dark above. This specific configuration, later formalized by the researchers Dorian Abbott and Eric Switzer in a 2011 paper, was given a name that captures the idea with unusual precision. They called it the Steppenwolf hypothesis, drawing on the image of a lone wolf surviving, self-sufficiently, far from any pack, sustained by nothing but its own internal resources. According to Abbott and Switzer's modeling, a rogue planet with roughly the mass of Earth, wrapped in a hydrogen atmosphere of sufficient thickness, could maintain a liquid ocean beneath its ice for timescales measured in billions of years, not decades, not centuries. Billions of years, powered by nothing but the same slow radioactive decay already occurring quietly inside Earth's own crust and mantle at this very moment. For context, this is not a new or unusual physical principle being invoked for the first time. It is the same basic mechanism that scientists already point to when explaining the confirmed subsurface oceans of Europa and Enceladus, two icy moons orbiting Jupiter and Saturn respectively. Both moons sit far beyond the reach of any meaningful solar warmth, and yet both are believed, based on direct spacecraft observations, to harbor liquid water oceans beneath their frozen outer shells. In those specific cases, the heat comes primarily from a different source, tidal flexing caused by the gravitational pull of their parent planets, rather than radioactive decay. But the underlying principle is identical: heat generated internally, trapped beneath an insulating shell, can sustain liquid water in complete darkness, far from any star, for extraordinarily long stretches of time. What Abbott and Switzer proposed is that a rogue planet, entirely free of any parent body, gravitational or stellar, could achieve the same outcome using only its own radioactive interior and a sufficiently thick atmospheric blanket. No tidal flexing required, no sunlight required, no star required at all. Sit with the picture this creates, because it stands in direct, almost startling contrast to everything described in the previous section. Picture once again the same planet from before, its atmosphere already frozen and fallen to the surface as layers of solid nitrogen and oxygen, its surface locked in temperatures within a few dozen degrees of absolute zero, silent, still, and dark. Now picture what Stevenson, and later Abbott and Switzer, suggest might exist beneath that frozen exterior. A thick, insulating layer of hydrogen gas, itself frozen solid at the surface but transitioning. Deeper down, back into something more fluid under pressure. Beneath that, warmth. Not warmth from a star that no longer exists. Warmth rising slowly from the planet's own interior. The same radioactive decay that has been running quietly inside rocky planets since the solar system first formed, still running, still producing heat, with nowhere fast to escape. And beneath that warmth, if the modeling holds, water. Liquid. Moving, however slowly, beneath miles of frozen crust, untouched by starlight for longer than most stars manage to survive, sustained entirely by processes already occurring, right now, inside the interior of every rocky planet in every solar system across the galaxy. In simple terms, the surface tells one story: cold, dead, frozen beyond anything survivable. But the interior, according to this modeling, may tell an entirely different one: warm, wet, sealed away from a universe that no longer knows this world exists at all. This possibility remains, it must be said clearly, a theoretical model rather than a confirmed observation. No rogue planet has yet been directly examined closely enough to confirm a hidden ocean beneath its surface. The Steppenwolf hypothesis describes what the physics allows, not what has been directly witnessed. But the physics itself, the radioactive decay, the insulating atmosphere, the precedent already confirmed on Europa and Enceladus, is neither speculative nor exotic. It is simply physics already understood, applied to a new and stranger context. If even a fraction of the free-floating planets estimated by surveys like Sumi's actually meet these conditions, thick atmosphere, sufficient radiogenic mass, then the galaxy may currently contain oceans, plural, sealed beneath ice, drifting through starless space, warm and dark and entirely unreachable, existing in complete isolation from everything else that exists. The next question follows naturally from this, and it is the same question that has quietly shaped the search for these worlds from the very beginning. If oceans like this exist, hidden beneath frozen shells, on planets with no star to illuminate them, how would anyone ever find one at all? If oceans like this exist, hidden beneath frozen shells, on planets with no star to illuminate them, how would anyone ever find one at all? This question sits underneath every claim made so far in this story, and it deserves an honest answer, because the honest answer is humbling. Consider what detection actually requires under normal circumstances. Most planets discovered in the galaxy so far have been found because of their star. Either they pass in front of it, dimming its light slightly at regular intervals, or their gravity tugs the star itself into a small, detectable wobble. Every conventional method of finding a planet depends, one way or another, on the presence of a nearby star to provide a reference point. A rogue planet has no such reference point. There is no star to dim, no star to wobble, no light to reflect back toward a telescope pointed in its direction. In simple terms, most of the tools built to find planets are built around an assumption that quietly fails the moment a planet loses its star completely. What little a starless world can offer in terms of detectability comes down to one faint, fading signal: its own residual heat. A planet like PSOJ 318.5-22, discussed earlier, remains detectable only because it is still young, still radiating leftover warmth from its own formation, glowing faintly in infrared wavelengths that a sufficiently sensitive telescope can register. But that glow fades over time. Billions of years after formation, once a planet's residual heat has mostly dissipated into the surrounding dark, even this faint signature becomes too weak to detect with current instruments. This leaves microlensing as the primary method available for finding older, colder, rogue planets, the very method that produced Sumi's landmark 2011 estimate. And microlensing, for all its value, comes with a limitation worth stating plainly. It is a method built entirely around chance. To put this in human terms, imagine trying to identify everyone who has ever walked past a single window, using only the brief flicker of shadow each person casts as they cross it, at some unknown moment, on some unknown night, with no way to ask any of them to walk past again. That is close to the actual situation astronomers face. A microlensing event, once it happens, does not repeat. The rogue planet responsible for it continues on its own path through the galaxy, and the specific alignment that caused the flicker will likely never occur again in any human lifetime, or in any lifetime at all. This means every confirmed detection is, in a very real sense, a single, unrepeatable data point. Astronomers do not get a second look. They do not get to point a follow-up telescope at the object later and confirm additional details. They have one flicker, one measurement of duration and brightness, and from that single flicker, they infer a mass, a rough distance, and very little else. Consider what this means for the broader population estimated from these events. Every number describing how many rogue planets might exist in the galaxy is built from an accumulation of these brief, singular glimpses, extrapolated statistically to describe a population that, individually, remains almost entirely unseen. There is a real, well-documented precedent for exactly this kind of fleeting, almost missed detection. And it did not involve a planet at all. It involved something considerably smaller, and it demonstrated just how easily an object passing through the solar neighborhood could go unnoticed entirely. In October of 2017, the Pan-STARRS 1 survey telescope in Hawaii, the same instrument responsible for discovering PSOJ 318.5 minus 22 years earlier, detected a faint object moving through the solar system on an unusual trajectory. Follow-up observations quickly revealed something remarkable. The object's path curved in a way that ruled out any origin within the solar system itself. It had arrived from interstellar space, passed briefly through the region near the Sun, and was already on its way back out, never to return. This object received the name Oumuamua, a Hawaiian word chosen to reflect its nature as a messenger arriving from a great distance. It became the first confirmed interstellar object ever observed passing through the solar system. Direct proof that material from beyond the Sun's gravitational influence does, in fact, cross through this neighborhood from time to time. What makes Oumuamua relevant here is not its size or composition, both of which remain debated among researchers. It is the circumstances of its discovery. Oumuamua was only detected because it happened to pass relatively close to the Sun and Earth during its transit, and because it happened to do so while a sufficiently sensitive survey telescope was actively watching that part of the sky. Had it passed through the solar system's outer regions instead, farther from the Sun, dimmer, slower to cross the field of view, it would very likely have gone completely undetected. Astronomers would never have known it existed at all. For context, Oumuamua was already gone on an outbound trajectory by the time it was found. There was no opportunity to send a spacecraft to intercept it, no way to gather more than a brief window of observations before it faded beyond the reach of Earth's telescopes entirely. It was found by chance, observed briefly by necessity, and lost again permanently, all within a matter of weeks. If a single confirmed interstellar visitor, passing directly through the solar system's inner regions, was nearly missed entirely, consider what this suggests about the countless rogue planets estimated to exist much farther out, in the vast, dark spaces between stars, with no reason to ever pass anywhere near enough to Earth to be noticed at all. In simple terms, finding a rogue planet is closer to catching a single flashbulb pop in a stadium during one specific second from somewhere outside the building entirely, with no way to know in advance where to point the camera. This is the quiet, honest conclusion this particular thread of the story arrives at. The galaxy, according to the best current estimates, may contain more starless planets than visible stars. Some of those planets, according to the physics described earlier, may harbor oceans sealed beneath their frozen surfaces, warm and dark and entirely self-sustaining. And almost none of them will ever be found, not because the search lacks effort or ingenium, because the physical circumstances of detection require a chance alignment that, for the overwhelming majority of these objects, will simply never occur within any span of time that matters to human observation. Consider what this means, extended outward across the full scale of the galaxy itself. Hundreds of billions of stars occupy the Milky Way, and by current estimates, an even larger number of starless planets drift silently between them. Unlit, unseen, catalogued only in the aggregate as a statistical inference rather than a confirmed and growing list. Each individual world exists in complete isolation from human knowledge, known only in the sense that its broader population has been estimated to exist at all. The galaxy, seen this way, is not simply a collection of stars connected by empty space. It is closer to an ocean far larger than anyone previously imagined, in which the visible stars are only the lit buoys scattered across its surface, and the true population beneath, cold, dark, and largely unmapped, remains almost entirely out of reach. The galaxy, seen this way, is closer to an ocean far larger than anyone previously imagined, its lit buoys scattered thin across a surface mostly dark. This raises one final, quieter question, and it is perhaps the loneliest one in this entire story. If a planet drifts long enough, does it ever find its way back? Does the dark ever end, even by accident? The honest answer requires understanding just how much empty space actually separates one star from the next. This is worth sitting with slowly because the emptiness involved is far more extreme than casual intuition suggests. Consider the nearest star to the Sun, Proxima Centauri, sitting roughly 4.24 light-years away. To put this in human terms, if the Sun were shrunk down to the size of a marble, Proxima Centauri, on the same scale, would be another marble sitting more than 600 miles away, with almost nothing but empty space filling the distance between them. No dust, no debris, no stepping stones, just distance, vast and uninterrupted, stretching in every direction between one point of light and the next. A rogue planet, once ejected, carries a fixed velocity determined entirely by the encounter that set it free. There is no star left to slow it down, and no star left to speed it up either. Its path, from that point onward, becomes a straight, unbending line, carried forward by nothing but the momentum it already had at the moment of departure, continuing indefinitely through the space between systems. For that path to intersect another star closely enough to matter, several extraordinarily unlikely conditions would need to align. The rogue planet's trajectory would need to pass, by chance, through the tiny, comparatively narrow region of space where a star's gravity is strong enough to capture rather than simply deflect. Stars themselves, despite their overwhelming mass, occupy only a vanishingly small fraction of the space surrounding them. Consider the numbers directly. The distance between neighboring stars, on average, is measured in trillions of miles. The stars themselves, by comparison, are pinpricks, smaller in relative terms than a single grain of sand scattered somewhere across an entire continent. In simple terms, a rogue planet drifting through interstellar space is moving through what is, for all practical purposes, an almost perfect vacuum of gravitational influence, occasionally passing near enough to a star to be nudged slightly, but almost never close enough to be captured and held in a new, stable orbit. Simulations modeling this kind of chance encounter, run by researchers studying stellar dynamics across the galaxy, suggest that a captured rogue planet is not impossible. It is simply exceedingly rare, requiring odds so narrow that across the entire multi-billion-year history of the galaxy, only a small fraction of ejected planets would ever experience it at all. For the overwhelming majority, the encounter that set them free is also the last significant gravitational encounter they will ever have. This means the planet's course, fixed at the moment of ejection, remains essentially permanent. Whatever direction it happened to be traveling when it crossed its star's escape velocity is, for all practical purposes, the direction it will continue traveling for the rest of its existence. No further course correction, no later encounter to nudge it elsewhere. Only the same straight, silent path, continuing outward through the same unbroken dark, for longer than most stars survive. Consider what this means measured against the lifespan of a star like the Sun, which will continue burning for roughly another 5 billion years before exhausting its usable hydrogen. A rogue planet, once ejected, will likely still be traveling along that same fixed path, long after its original star has gone through its own final transformation and faded from the sky entirely. The planet outlives the very star that once held it. There is something worth pausing on here, quietly, without exaggeration. A rogue planet does not simply lose its star once. It loses the possibility of ever having another. Not because nature forbids it, because the distances involved make it, in any meaningful sense, essentially impossible. The vacuum between stars is not simply empty. It is emptiness on a scale that renders reunion, for almost every ejected world, a mathematical near certainty of permanent absence rather than eventual return. And so the planet continues, cooling, its atmosphere already long since fallen and frozen across its surface, sealed in some fraction of cases around a hidden ocean warmed only by its own radioactive interior, sustained entirely by processes already occurring, somewhere, right now, drifting along a path fixed permanently by a single gravitational encounter that happened once, long ago, and will not happen again. It moves through the space between stars the way a lone traveler moves across an ocean with no shore in any direction. Not lost exactly, because a place cannot really be lost if it was never trying to reach anywhere in particular. Simply traveling, continuing, existing in a kind of permanence that has nothing to do with stability and everything to do with the sheer, overwhelming size of the emptiness it now belongs to. This is true as far as current evidence and modeling suggest, for the countless rogue planets already estimated to exist scattered throughout the galaxy. Worlds ejected from young, unstable systems billions of years ago. Worlds still being ejected somewhere, right now, as some distant system undergoes the same gravitational reshuffling that once, according to Nesvorny's modeling, may have claimed a fifth giant planet from the young solar system itself. Which raises one final thought, quieter than all the others, and closer to home than anything discussed so far. If this has already happened once, in this very solar system, billions of years ago, is it truly finished happening? Or is the arrangement currently overhead, stable and unchanging as it appears on any given night? simply the current chapter of a story that has not yet reached its final page. Is the arrangement currently overhead, stable and unchanging as it appears on any given night, simply the current chapter of a story that has not yet reached its final page? The honest answer is no. It is not finished. It was never going to be finished. Permanence was never actually on offer for this solar system or any other. Consider what lies ahead for the Sun itself, on a timescale that dwarfs anything discussed so far. In roughly 5 billion years, having exhausted the hydrogen fuel sustaining it now, the Sun will begin a transformation well understood by stellar physicists, documented through observations of countless similar stars, already partway through the same process elsewhere in the galaxy. It will swell. Its outer layers will expand outward, cooling as they do, turning the Sun into what astronomers call a red giant, a star large enough, by some estimates, to reach as far as Earth's current orbit or beyond. During this transformation, the Sun will also shed a significant portion of its own mass, blown outward in a slow stellar wind that thickens considerably during the red giant phase. This detail matters more than it might first appear. A star's gravitational grip on its planets depends directly on its mass. Reduce the mass significantly enough, and the grip loosens correspondingly. The same relationship between escape velocity and central body, described earlier in this story, now playing out across the entire solar system rather than a single planet. In simple terms, the Sun currently holding this solar system together will not always be as strong a hand as it is tonight. Billions of years from now, it will hold less tightly, by simple consequence of holding less mass. For the distant, icy bodies occupying the solar system's outer edge, the Oort cloud described briefly in earlier chapters of this subject, this loosening grip carries real consequences. Some of these distant objects, already sitting at the very edge of the Sun's gravitational influence, may find that influence weakening beneath them as the Sun sheds mass during its red giant phase. A comet or icy body already loosely bound at the faint outer edge of what the Sun can still hold may simply drift free during this transformation, joining the same population of starless wanderers described throughout tonight's exploration. Consider what this means, extended across the full arc of time available to any solar system. Ejection is not a single dramatic event, confined to one violent afternoon early in a system's history. It is closer to an ongoing process, quiet and continuous, capable of claiming a planet during a young system's chaotic infancy, and capable of claiming smaller, more distant bodies again, billions of years later, as that same system's central star finally begins to change. This is worth pausing on because it reframes everything discussed across this entire evening. The rogue planets described earlier, drifting alone through the space between stars, were not necessarily created only through violent, early gravitational scattering. Some fraction of them, current models suggest, may have been released far more gently, far more slowly, over the long, patient course of their star's natural aging. There is something quietly settling in recognizing this, even if the physics itself carries a note of loss. Every solar system, including this one, exists inside a kind of long, unhurried lease, granted by the gravity of its central star. And that lease has an expiration date written into it from the very beginning, in the mass and composition of the star itself. This does not mean anything alarming is coming soon. 5 billion years is a span of time that renders any human concern almost meaningless by comparison. life on Earth, if it persists at all across that unimaginable stretch, will likely be shaped by circumstances entirely unrecognizable by anything happening tonight. The point is not urgency. The point is perspective. Consider one final time everything this evening has traced. A planet loosened from its star through violent early encounters, the same mechanism modeled by Nesvorny in this very solar system's own deep past. A planet observed directly, drifting and glowing faintly in the data collected from Pan-STARRS 1. A population estimated through years of careful micro-lensing surveys that may number more than the visible stars of the galaxy combined. An atmosphere that falls, gas by gas, coldest last, until the sky itself becomes a frozen floor. And beneath that frozen floor, in some fraction of these worlds, the quiet possibility of warmth still rising, an ocean still moving, sustained entirely by processes already occurring, right now, inside the rock beneath everyone's feet. None of this required a star to remain in the story at all. That may be the quietest, strangest lesson buried inside everything covered tonight. A star provides light and warmth, and a familiar rhythm of day following night. But a star was never the only thing keeping a planet whole. Some of what a planet needs, it turns out, it can carry inside itself, indefinitely, long after every star it ever knew has gone. The night sky, seen this way, is not simply a field of stars, fixed and permanent, holding their planets in careful, unbroken formation. It is closer to a slow, patient sorting process, still underway, still releasing worlds quietly into the dark. One gravitational encounter, one stellar transformation at a time. Some of those released worlds carry oceans, some carry only frozen silence. All of them continue, regardless, along paths that will not bend again. And somewhere among them, drifting right now, entirely unremarkable in the vastness surrounding it, is the fifth giant planet that once orbited alongside Jupiter 4 billion years ago, in a solar system not yet finished rearranging itself. Still traveling, still cooling, carrying, perhaps, beneath whatever remains of its surface, the same quiet warmth that keeps this very planet's own interior from ever going fully cold. You are listening to these words from the surface of a planet that has, so far, kept its star. That is worth noticing, quietly, before anything else. Not because it is guaranteed, because it has simply not ended yet. Somewhere else, right now, in some other corner of this galaxy, a young system is going through exactly what this solar system went through 4 billion years ago. A gravitational encounter is deciding, in that moment, which of its planets get to stay. One of them, when it is over, will not. That planet will not vanish. It will keep existing, the way every rogue world described tonight keeps existing, carrying its own weather into stillness, its own sky into snow, its own quiet furnace burning on beneath layers of ice that no sun will ever touch again. It will drift, fixed on a single unbending path. For longer than the star it left behind will even survive. What happens when a planet is ejected from its solar system, then, is not an ending in the way it first sounds. It is closer to a change of address, permanent and irreversible, from a world with a ceiling of light to a world with no ceiling at all. Some of these worlds, sealed and dark on the outside, may be carrying oceans no one will ever see. Warm in the one place warmth was never supposed to reach. Held there by nothing but the same patient decay already happening, tonight, in the rock beneath everything familiar. Picture one of them now, not close, not urgent. Simply out there, somewhere between the stars visible tonight and the ones too faint to name. Moving through a darkness with no edges, carrying its small, hidden warmth like a candle sealed inside a house with no windows left. It does not know it is alone. It does not know anything at all. It simply continues, the way physics continues, indifferent to whether anyone is watching, indifferent to whether anyone ever will be. And so, somewhere in the dark tonight, a planet drifts on, carrying its ocean and its silence and its unbroken, ordinary permanence into a night that has no morning waiting on the other side.